Hello, my name is George Cadman, and this is the Digital Sampling Lab from section A11X. For an introduction to the lab, we need some background info. Some important equations is the waveform equation, which depends on the time. The frequency equation is equal to 1 over the period, and then the sampling frequency equation and Nyquist sampling equation state that your sampling frequency needs to be twice the maximum frequency of your sample. The motivation for this lab is to understand how waveforms and frequencies can be recorded and analyzed. My objective for the lab will be play a known song and see how the notes are mapped in the power density versus frequency domain. Some objectives is to gain familiarity with digital data acquisition of time-varying signals and to explore issues in sampling, filtering, and digitalization of errors. So, for the prior to week 2 data, we had to analyze tracks and then determine the waveform type and the peak frequency. Listed in the table is 11 tracks with waveform types ranging from single sine waves, triangle waves, square waves, ramp waves, sine with noise waves, sum of 3 sines waves, product of 2 sines, and sine wave of a sine wave, with the peak frequencies listed on the right. So, for the waveforms, here we have a visual representation of what they look like. Prior to week 3, we had to validate the microphone and record the relative response. The procedure was to measure microphone response to 5 different frequencies with the microphone and audio jack. The frequencies I chose was 200 Hz, 1000 Hz, 3000 Hz, 8000 Hz, and 10,000 Hz. Below is a table that includes the frequency numbers, the power from the microphone, the power from the direct connection, and the relative response, which is equal to the power from the microphone divided by the power from direct connection. As you can see, the relative response starts low and increases as the frequency increases until you get to a maximum frequency amount where it starts to drop off. Below is a graph of the relative response versus the frequency, where you can see the trend I just talked about, where the relative response increases with frequency until a rapid drop-off. So, for my experiment, what is the equipment we're going to need? We're going to need a LabJack T4 DAC, the microphone, a 3.5mm audio breakout adapter, a USB-A to USB-B adapter, male-to-male jumper cables, and a speaker to play audio. So for the procedure of the experiment, I plan on connecting the LabJack T4 DAC and 3.5mm audio breakout adapter, set the sampling rate to 20,000 samplings per second to ensure proper sampling due to the Nyquist theorem. I'm then going to play the simple audio of Mary Had a Little Lamb into the microphone, only the first half, 13 notes, and the notes of the songs are as follows: A, G, F, G, A, 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 G, 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 A, C, C. I then plan to analyze the power density versus frequency, and the notes should cause peaks at the relative frequency. Here's a video of the recording of the song, and you can see the frequency spikes when each note is played. So, for my experiment results, the song has 4 unique notes: C, A, G, and F. C has the highest frequency, and F has the lowest. The power density versus frequency graph clearly shows 4 peaks throughout the experiment, and you can see that on the right. The graph below is highlighted with the highlighter to show the distinct peaks. These frequencies correspond with the 4 unique notes. C was around 2700 Hz, A was around 2250 Hz, G was around 1550 Hz, and F was around 800 Hz. So, for my conclusion, the pitch of the sounds around us are determined by the frequency of the wave. Graphing power density versus frequency of a sample can show unique frequency spikes. Power density versus frequency is not a good way of describing at what time the sounds were made. And a very low frequency will generally give a lower relative response when compared to a middling frequency. Some possible error sources in my lab include background noise, such as road noise or fans. And also, the first few seconds of data was omitted due to significantly higher values than the rest of the dataset. Also, each sample taken with the microphone was played from a slightly different distance, which could slightly skew the results. Now I'm going to include the lab notebook. Thank you.